Hello, I'm Richard, and this is a video on an exploit I've written for the Linux kernel. Originally, I was going to do 3 videos, sort of going through each stage of the exploit. That didn't go so well, so I've skipped to the final stage where I execute a ROP chain and escalate privileges. So the bug that I exploited, it's the first bug I've ever exploited, which is a bit unusual to target the Linux kernel as the first bug, but I'm quite familiar with Linux, having worked with it for a number of years. And so anyway, this bug has been exploited before. It was originally exploited in the Google kernel CTF on the mitigation instance. So there's another exploit out there which is more advanced than mine, I'd say. And I decided to re-exploit it without looking at the original exploit, because I mean it wasn't available when I started trying to exploit this, and work through it and see what is required to exploit a bug on modern Linux targeting a system with a decent monetary reward, and see what's involved in doing that. And also another advantage of targeting a bug that's already been done, but nonetheless is a real bug, is that I know to push through and keep going if I get stuck. One thing I was worried about is if I just just try to find a bug and then exploit it, I'm not really going to have much instinct about how exploitable it is. So I could just be bashing my head against a problem that's unsolvable, or would require new techniques. Something that is, as a beginner, I'm just not going to do like in any reasonable time. So anyway, I exploited it. What you can see in front of you is the output in the middle of the exploit. It's currently been stopped by the debugger at the bit just before the ROP chain starts. So I'm going to try and talk through the ROP chain. But first of all, I'll just briefly explain how we got to this point. The bug is in the TLS subsystem for TCP sockets. The Linux kernel has this concept called user level protocols that sit on top of TLS sockets. And there's a problem where the ULP data, or the TLS context specifically, is copied when a listening socket with a TLS context accepts a connection. But during the cloning of the socket and copying the TLS context, the kernel just copies the TLS context pointer, which it shouldn't do. It should actually clone that object and create 2 separate objects that is then passed to the child socket, because when the child socket closes, it frees that context, but the parent socket still has a copy of that pointer. And so because the parent socket, which is in a listening state, has a copy of that pointer, you can reuse that pointer, or you can create multiple sockets, accept multiple connections, and reuse the TLS context as part of each of those child sockets that were accepted, which is actually what I do. I have 2 different sockets that I accept, and one of those sockets I eventually send a message on, a control message, which is where the ROP chain starts. Okay, so I have an article on the bug as well, which you can read to get an idea of like what causes the bug and how to reproduce the exploit. An interesting thing is that most likely the reason this bug occurred is because usually if you put a TLS context on a socket, or you put a ULP on a socket, you have to do that when the socket is connected, or with TLS you have to do it when the socket is connected, and the socket state is set to connected. But it turns out that it's possible to set the socket state back to unconnected. Should we go a little up here a little way? It can be set back to unconnected, but using the connect system call. So you can set the address to unspecified address and AF unspec, and it'll set it back to unconnected, which is unexpected. And then once it's set back to unconnected, even though it has a TLS context attached to it, you can then go and listen on that socket. The fix for this particular, well, the fix for now is to make it so you can't call listen if there's a user level protocol that doesn't implement the clone. Another fix for TLS could be to actually implement a proper clone when you accept a connection. But okay, so that's the bug. It's actually relatively straightforward to reproduce the error, but it's kind of a confusing bug to get your head around to begin with. But otherwise, like compared to some other bugs, it's pretty easy to reproduce. You can do it reliably. There's no race conditions or anything like that. Then the next stage in that is to reuse the memory for something. I reused the memory with fuse and set extended attribute, which again I explained that a bit in the blog post, and also there's lots of other articles out there and how you use set extended attribute to overwrite memory. So we use set extended attribute to overwrite the TLS context, and we can then corrupt values from the context. We can get internal kernel pointers from the context, which allows us to break address layout randomization, and eventually we can write a ROP chain into the TLS context, and then we can set the stack pointer to the TLS context and start executing the ROP chain. Okay, so on the left we have GDB with the pwn debug extensions. Pwn debug gives us this like nice layout with at the top you've got like all the stack variables up here. And like it even tries to dereference pointers that are in the stack variables, so we can see that this send message points to this instruction somewhere in memory, and then there's some other pointers that point to various locations. And then we've got disassembly output, which is really useful when we're looking at a ROP chain that we're trying to get started, and the source code location. And at the bottom here we have the stack, which is currently the real kernel stack. We haven't changed that yet. And then we've got the backtrace at the bottom here. So we can see that we've entered the kernel through the send message system call, and eventually we've ended up in TLS process C message. So let's just go and look at that. Where is it? Okay, so control messages are like a special message that you use just to like change a setting or something on the socket. In this case, it can be used to change the TLS record type. We don't actually do that, like we never actually manage to set the record type, because instead what we do is we overwrite this function pointer here, which is part of the TLS context, and this is the point where we start our ROP chain. Okay, so let's have a look at where we are. Let's move this into the middle. Okay, so expand that a bit, redraw the context, right. Okay, so currently we've just come into TLS handle open record. Again, it's discussed in the article a bit more how we managed to get to this point. And we're just going to step into this, step over dereferencing the context. TLS is pending record. We overwrote some memory in the kernel. If we step into this, we can see that, yeah, in the exploit, we overwrite the pending open record frags to a truthy value. So we can actually print that. You can see it have set it to the full byte. Did that in the exploit, and regardless of whether we actually have any pending fragments, we know that we're going to call push pending record. Usually, in order to get this value set, you'd have to manufacture a situation where there's TLS record fragments or something waiting to go. There aren't really, we just overwrote it. So let's step to the next location. Okay, continue to step over that. Now we're going to carefully step instruction by instruction into this function call, because if we continue to do a normal step now in the debugger, like a source line step, the debugger is going to get horribly confused, because actually this function pointer points to the beginning of my ROP chain. Well, it actually points to, let's have a look. Let's context push pending record. Let's just look at that. Just thinking about it. It points into Intel PMU LBR disable all. So clearly it doesn't point to the right place. It should point to something like TLS push pending record or TCP push pending record. It shouldn't be pointing into whatever this Intel specific stuff is, because I've set the memory address there. Okay, so let's just step into that with the you can see now in the middle section that we're stepping instruction by instruction, and we're about to call something. We're about to call a function called x86 indirect thunk array. Okay, so thanks to Spectre and Meltdown and the other side channel attacks and whatever, a bunch of stuff. When you have a function pointer in the Linux kernel, it doesn't just call that function pointer. It calls like this bit of code that is inserted by the compiler and specified by the Linux kernel, to my knowledge, that does some sort of indirection so that the CPU can't speculate on this and allow various side channel attacks. I mean, it's been some time since I looked at all that stuff. All I know is that's why it's here, and that's why we have this slightly weird thing going on. Okay, so we're moving now into this function, indirect thunk array, and we'll carefully step into this. I don't want to accidentally step into the actual bit. Okay, right, it's moving Intel PMU LBR into the top of the stack. Okay, so let's just do one more step and then we'll be on return. Okay, so you can see it's moved the start of an instruction onto the top of the stack, and now because it's in R11, we can see that the memory it's pointing to it has the move RSP, move racks into RSP. The RSP register is the stack pointer register. So this register RSP, this controls where our stack is located, and the instruction that we've pointed the push pending records function pointer to, because it's not really a function, it's just a location in memory. What this is going to do, it's going to move RAX, which the racks register just so happens to include another location in context, okay, in TLS context, because where did I set RAX? Where did that come from? Okay, I'm sure it'll come back to me. Right. So, where the hell did racks come from? One of these should be the context. Okay. Ah, yes. RAX. This points to TLS context. And it points to TLS context purely by good luck, because previously in this function here, TLS handle open record, we dereferenced the TLS context in order to get this function pointer. At this point, it's no longer needed to have a reference to TLS context because the function pointer has the arguments are the socket and the socket's flag. So we don't actually need context. It just so happens that the compiler kept it in that register, which then means we can use it. So we have used it to do a stack pivot to TLS context, which is what we're about to do with this little bit of code here, which moves REX into RSP. So if we look down here, we can see the stack as it currently is, and then we're going to step into that instruction. Okay, let's step again. Okay, one more time. Oh, I should just mention that what's happened here as well is the indirect thunk array function. It put our function, our fake function pointer onto the top of the stack and then called ret. And the ret instruction jumps to the location on top of the stack and pops the stack, removing the top item on the stack. So this is really important for return-orientated programming, because this means that you can create a fake stack, put a bunch of code locations on the stack, or like fake function pointers, whatever, and then you can find sequences of instructions just before a ret, and what will happen is it will execute those sequences just before the ret, called a gadget, and then the ret will keep jumping to yet another item in the chain. So you can construct like an assembly program comprised out of these little chunks of assembly instructions before a return. Okay, so that's, like a really bad description of return-orientated programming there for you. Okay, so now we're going to just finally put racks into RSP, and we see that, okay, now the stack has changed. It's changed to our ROP chain, except that, okay, the first thing we're going to do before like trying to execute our code which escalates privileges is we're going to do another stack pivot where we jump further down the ROP chain, which if I print, do we still have a, if I, okay. I'm going to try printing the context. Okay, so this is the TLS context, and we're going to see why we execute this further jump. At the bottom here, we have part of our ROP chain should be down here somewhere, and also, yeah, this code here is probably the ROP chain. You can see it's trying to interpret it as like the IV and key and salt and stuff that make up the cryptographic information. But if we look in the middle of our ROP chain, so at the top here, we have prot info, which I overwrote with the first item which pivots the stack. And we can overwrite prot info and call send message. It doesn't matter, like it's not really used for anything if we're just doing a control message. But after that, we have push pending record, which is actually where we began our ROP chain. So we can't just overwrite this bit with the rest of our ROP chain. And we've got somewhere down here. There's more stuff here we really don't want to overwrite. In particular, this bit. So what we do is we just jump past it. We jump past the mutex as well. I think this is actually used in some of the code we're using. So we jump past that to a location where we can just do whatever we like with the add OX90 to RSP. And I think we actually do this twice. So if we carry on stepping again, what do we have now? Yeah, we're going to do it again, I believe. Yes, we're going to add another value to RSP. The symbol we're actually adding to it is ksymtab fuse dev operations, but okay, whatever. Gonna step into that again. Gonna have to return. So this is a ROP gadget we're executing right now. Had to think about that for a moment, probably because we're stepping into like some code which is not that close. And what are we doing? We are adding more to RSP, so we're doing another stack pivot. I guess we do it 3 times then. And when we return this time, and now we're actually into the ROP chain proper. So I go to my exploit. Okay, so this is what the ROP chain looks like when I'm creating it inside the exploit program. So what we do in our ROP chain to escalate kernel privileges is we call a couple of kernel functions that escalate kernel privileges. We call prepare kernel creds offset and commit kernel creds offset. Prepare kernel creds copies the default kernel credential structure, makes a few changes to it, and then this structure like gives you full root credentials in the root namespace. And then we pass that to commit kernel creds, which makes those credentials the processor's current set of credentials. And I think I got quite lucky while constructing this ROP chain. So anyway, right, we're moving R8 into RDI. That's not important. I had to do that. Oh, sorry. I actually then move that into racks as well. Okay. What's in R8, I wonder? It's 0. Right, okay. So the way that I set RDI to 0, because prepare kernel creds, let's just try getting that function up. Prepare kernel cred. Oh, not creds, cred. It takes an argument of daemon, but you can set that to null, and it'll just use the initial credentials. So in x86, the RAX register, the RAX register, is the first argument to a function. So we want to set RAX to 0. Currently it's set to the context. So we just want to find a way of setting it to 0. The first gadget I found that could do that first moves R8, which happens to already be 0. The R8 register already just happens to be 0, and we move that into RDI, and then we move RDI into racks. Like, we don't really want to set RDI or change it, but it just so happens we have to, unless there's a gadget I didn't see, which is completely possible. So I'm going to do that. So we can see at the top here it's changing the register values, and now racks is 0. And now we're going to jump into an actual real function. So if we step into this, here we are, we're in prepare kernel creds. So now I'm going to switch to stepping over source lines, as this is quite a long function. You can see here it's allocating the credentials. Hopefully that goes okay. So yeah, daemon is our racks1, and if we print that, we'll see, hopefully see that it's 0. Yeah, it's 0. Took a long time though, GDB, I don't know what it's trying to do, but okay, step over that. Next, get creds. Okay, let's step into that just to see. Okay, so get cred. Okay, this is just yeah, it's just increasing the counter for it. Let's just step out of that. Okay, so we've got a new credential that's basically just a copy of init cred. So if we print init cred, yeah, we can see that UID is 0, GID is 0, blah blah blah. Importantly also, the user namespace is the default and that sort of thing, so we don't then have to come out of the username, like out of a nested user namespace if we're in one, inside a container or NSJ or whatever. Okay, so let's step over again, blah blah blah. I don't dare type bin to step out of the function. I want to start stepping into want to start stepping by each assembly line when we get to the end, which is where we are now. So we're now at the end of the function. We're moving RBX into racks, which is really good, because again the return value for this function is our new credential, and the racks register is the first argument for the next function. So we don't have to do anything in between calling these functions. It's already set up to call the next function directly. Okay, so I'm going to step over this bit. It's now restoring some registers from the stack. So it actually wrote into TLS context, which is something to bear in mind. That's actually another reason to do a fairly large stack pivot down the stack, is that it pushes some values to the top of the stack, so you want to have room at the top of the stack to hold those values. And now it's restoring those values before the next function call. It's a good thing it restores RBX, which we'll see why later. Okay, so now I'm going to jump into commit creds. And this is it. We're now about to escalate privileges. So let's start stepping over this again. Yeah, blah, blah, blah. Some sanity checks. A whole bunch of stuff goes on here. Yeah, so it's just set the privileges now with our CU assign pointer. Doing some other stuff. Blah, blah, blah. Oh, whoa, 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 whoa. Okay. Where are we? Put cred, okay. Step over that. And we're in the final section again. So at last it sets EAX to 0 because the return value was successful. Then we're going to pop a bunch of stuff from the stack. And let's get down to the ret. Okay. But our ROP chain is not finished yet. Let's go back and have a look at the exploit. So, okay, so this point here we can see we commit kernel creds. And then we've come to the point now where we want to return to the original location where we started the ROP chain. So if we go to TLS main. So what we want to do now is return from push pending record, or our fake push pending record. And to do this, we need to restore the stack to what it was originally. We can't just return with the stack still set to TLS context, because there's a whole bunch of stuff we need to do after returning from here in order to return to user land, and there will be a whole bunch of stuff saved on the stack to for all of the previous functions we've called in the function change. So what are we going to do? We're going to restore the stack from one of the Corley saved registers. So previously I mentioned RBX. The RBX register happens to point to a value that was on the stack. So let's just step into this. Okay, so we can see here that I found a gadget which moves RBX into racks, and as you can see in the Zig source code, as I've, whoops, oh no. Okay, as you can see in the Zig source code, I noted that the value of RBX was the original stack pointer plus 8F. So if we, right now, if we just add, if we subtract that value from there, this should give us the original value of the stack pointer. And we're going to do that in assembly in our ROP chain in a slightly roundabout way. So first of all, we put RBX in racks, and then we put we actually just pop some random value into RBX. That was not desirable. It's just something that had to be done, I think. So On the stack, we can see that I've got my value that I set there, which is like obviously not a serious value. That gets popped into RBX. And then we jump to the next gadget, and then we push racks onto the stack, and then pop RBX onto the stack. So this is like a very roundabout way of moving RBX into moving racks into RBX. The reason we're doing this is because we need to keep RBX's original value. So what I'm doing here is I'm already cleaning up after ourselves, even though we haven't actually done the calculation yet. So okay, so now we've restored RBX back to the proper value rather than my joke value. Okay, and then we pop RSI. So on the top of the stack, I set the offset that we need for restoring the stack pointer, and I'm going to pop that into RSI, into the RSI register, which is just a general purpose register. And finally, we can subtract RSI from racks. So there's no function that'll, there's no more like direct way to do that. That's the best gadget I found as far as I know. So once we do that, yeah, we can now see that racks has been set to this value, which is the original stack pointer, and we can tell that because the memory location it's pointing to is inside TLS process C message, which is where we entered the ROP chain. So what have we got to do? Last thing we do is, okay, we finally set RSP to racks. And let's do one final step out of this Intel PMU function, which I have no idea what that does. And we're back in the proper kernel. Okay, so at this point, I'm just going to continue because we've done it. We've, yeah, and there we go. It's finished. That's it. The exploit is over. I actually ran the exploit when it was already the root user, but I have posted a different video where it's actually escalating privileges. And that's the end. Yeah, that's it. It's rather anticlimactic, really. Maybe at some point I might try to discuss the rest of the exploit. The problem is that trying to trace the exploit's execution through the debugger confuses the hell out of me. So yeah, we'll see. I also would like to replace fuse with something that doesn't require, that's not so easily mitigatable, and I want to look at the original exploit that uses some clever methods. Yeah. So goodbye. Thank you for watching this video. Please check out the blog post, and yeah, that's it. I'm done. Finished.